Hi, my name is Keisuke Okumura, a research scientist affiliated with Cambridge and AIST in Japan. In this video, I will talk about multi-agent pathfinding, MAPF. MAPF is a key technology for upgrading various multi-agent multi-robot systems, including warehouse automation. It gets gradually popular, but the number of researchers is still limited. So now might be the perfect timing for you to start studying MAPF because you have a high chance of becoming a future star in multi-agent multi-robot systems. So the aim of this video is to invite you to the frontier of this field directly. I want to clarify that I do not intend to create a tutorial. If this is your first time with MAPF, I think it may be better to check out the tutorials available online. For example, there is mapf.info, which summarizes various materials in this domain, so it is worthwhile to check it. With this in mind, in this video, I'll talk about upgrading multi-agent pathfinding for the real world, which summarizes recent research efforts of me and my collaborators. The talk includes combinatorial search aspects as well as machine learning and robotics. This talk is based on my invited talk at Euro MAPF held in conjunction with ECAI 25 held in Bologna, Italy. All right, let's begin. I kick off my video with this one. Nowadays, factory automation with multiple robots is becoming ubiquitous. And this is a video that illustrates what happens in Okedo's warehouse. Okedo is a British company, and you can see that hundreds of robots are in motion, and these robots carry packages to specified bins. Clearly, compared to manual human labor, such systems with multiple robots can be much more efficient and much more scalable. However, to elicit the power of such systems, it is very important to navigate multiple robots while avoiding collisions and redundant motions. Such multi-agent navigation programs can be seen in various applications. Here I show some examples: intersection management, drone shows, delivery services, games, or multi-robot assemblies. And all these examples need to navigate robots while avoiding collisions, deadlocks, live locks, congestions to efficiently complete tasks. Then the question is, how can we achieve efficient multi-agent navigation, right? Typically, there are two ways: centralization or decentralization. Centralized methods assume a central component that determines everything. In contrast, in decentralized methods, each agent or each robot determines its own action using the observation or some means of communications. And when we talk about scalability, people believe that decentralization has a significant advantage over centralization. In fact, decentralization is very, very powerful. I here present two examples of decentralized navigation systems, one from Tokyo, another from Amsterdam. And these examples are very impressive and demonstrate the power of decentralization. So yes, it seems to be promising to establish efficient multi-agent navigation via decentralization. But when we talk about large-scale automation, I'm a bit suspicious about decentralization. To share my concerns, let's have a look at delivery robots in restaurants. This cute robot has been already deployed in casual restaurants in Japan. This delivery robot is navigated by a decentralized manner. It works quite well. Okay, cool. But when multiple robots are used simultaneously, it can potentially cause deadlock situations. In the right movie, 3 robots are stuck and stop their operations. This is a kind of inherent limitation of decentralized systems. Indeed, such a miscoordination is not rare. The left example is a leak footage from Amazon warehouse where 2 robots face with each other and they are continuously failing to resolve live lock situation. On the right-hand side, this is a picture from Sao Paulo showing a gridlock of transportation system. There's no easy way to resolve this gridlock, right? So miscoordination of decentralization is very, very problematic. That's why I'm fascinated by centralized large-scale automation. With appropriate centralized designs, we can guarantee some nice properties such as safety or liveness. Moreover, we can maximize the system's performance. And this is an exactly multi-agent pathfinding program, MAPF. What is MAPF? Well, it is a graph pathfinding program for multiple agents. Formally, given a graph and a list of start goal pairs, we want to find a list of collision-free paths, assuming that each time step, each agent can move to an adjacent vertex. Ideally, we want to find near-optimal solutions within practical time frame, but of course, optimization is in NP hard. And this is indeed a good abstraction of various practical applications, such as warehouse automation. So if you have nice technologies to solve MAPF, then they can upgrade these multi-agent, multi-robot systems. That's why we are putting a lot of research efforts to this domain. And this is a visualization of academic research efforts to MAPF. I searched the number of papers using keywords such as MAPF, multi-robot path planning, and so forth. In 2010, there were only 494 papers, but at the end of 2024, we have now over 9,000 papers in total. This is not linear increase, rather it seems to follow exponential curve, so the community is growing. And since we now have almost 10,000 papers, I want to raise this question. Are cutting-edge MAPF studies ready for the real-world applications? And I want to say almost yes. And in the remaining of this talk, I try to convince you about my answer. First, we need to organize how to use MAPF in realistic situations. Practically speaking, we want to embed MAPF into feedback control loop. And this is a visualization. We have a task query and a MAPF planner, and plan goes to the actual systems, such as warehouses. And we repeat this process again and again. Of course, we need to consider a bunch of aspects to realize this feedback control, because typical academic research on MAPF assumes a grid world. It's very simplified. Meanwhile, real agents or real robots have complicated action models. They also work in wild environments. For example, robots usually have an orientation. They might have more capable dynamics or limited dynamics. Not only that, there are communication delays, task interaction, heterogeneity, and such like that. So at least we need to consider two challenges to realize MAPF feedback control loop. One, robot dynamics. Robots are in physical space, so they need to follow physical laws. The second challenge is to incorporate uncertainties. Robots might get delayed or might deviate from their plans, right? So the robot dynamics and uncertainties should be incorporated into MAPF planning. However, uncertainties make MAPF significantly challenging. To share some flavors, let me introduce my old study, a variant of MAPF. This is a graph pathfinding program to find deadlock-free solutions. And we have agents, goals, and solution paths are shown. And this solution looks a bit weird, right? Why not this guy takes the shortest path, like this one? However, this detour is actually necessary to be delay tolerant. On the right-hand side, I show possible transition flows of configurations, and the solution actually ensures that all possible transitions eventually converge to the goal configuration. And I really like this program because this program explicitly overcomes timing uncertainties with actual systems. right? Once you have solutions, it is very easy to deploy with actual robots. However, when we did complexity analysis, it turns out that finding a solution is NP hard. Not only that, verifying a solution is NP complete. This means that if we have a solution candidate, we cannot be very sure about its feasibility in an easy way. In short, uncertainties make MAPF intractable. So we need to think about uncertainties, but this is hard. I almost give up for this direction. Instead, let's iterate this feedback loop more frequently. My belief is that sufficiently quick replanning conquers uncertainties. This is because if anything bad happens, then we can immediately incorporate such accidents by quick replanning. But to do quick planning, we need to solve MAPF quickly. And that's why quick MAPF methods are key for practical deployments. Quick MAPF planners are good because they should be computationally lightweight, and therefore quick algorithms are also scalable for the number of agents. All right, now I think I convince you of the necessity of quick and scalable MAPF methods. But there are a bunch of MAPF algorithms. Are they really not scalable? I first try to answer this question. The following slides include a quick summary of several MAPF methods. The explanation will be very minimal because I do not aim to do the tutorial. Rather, I will explain these methods to highlight the recent progress in this domain. Okay, I'll start from ESTER. To derive a solution path, ESTER is the most fundamental AI technique. And to derive a solution path, it maintains a search tree. At the beginning, the search tree only contains the start vertex. Then ESTER creates successor nodes. And in the next iteration, ESTER selects a node based on some criteria and creates the successors. And this process is repeated until reaching the goal configuration, goal vertex, and once found, we can obtain a solution path by backtracking. Done. And we can use this scheme to solve MAPF. How to do that? In this example, there are two agents, and their goals are represented by colored boxes. We can create successors of this initial node by moving the blue agent or the red agent or both agents, like this. The second row illustrates several examples. ESTER then picks one node following specific criteria and applies the same procedure. And this procedure continues until finding the goal configuration, and once found, backtracking. Done. So ESTER can solve MAPF. Now, let's think about theoretical properties, completeness, and optimality of the solution. More precisely, complete algorithms return solutions for solvable instances in finite time. Otherwise, they should report the non-existence. Optimal methods always return solutions having minimum costs. And these properties are fundamental, and we want to achieve both. And talking about ESTER, it is complete and optimal if the heuristic is admissible. So ESTER has ideal properties. Okay, what about empirical performance? There is a widely used benchmark to evaluate the performance of MAPF methods. And on the left side, I will show the percentage of solved instances versus the runtime. Now, let me introduce the result of ESTER. Well, it solves 0.0%. Bad news, we cannot solve MAPF with a naive search scheme. Why ESTER is bad in performance? Because that ESTER creates a search tree, and each node in the tree has several successors. This number is called branching factor. What is the branching factor for MAPF? Well, MAPF has a 5 power of n, where n is the number of agents. And this is actually a huge number, and here I list several examples regarding the number of agents. And you can see that even with 5 agents, the number of successors is over 3,000. What about 100 or 1,000 robots? Ridiculous, right? So with A-star, it is almost impossible to create successors with many agents. Of course, there are A-star variants specialized to MAPF. It can solve more instances, like 0.4%, but its scalability is very limited. Okay, let's think about relaxing the completeness. Recall that complete algorithms return solutions for solvable instances, otherwise they should report the non-existence. And I want to drop this condition. This means that such methods cannot identify unsolvable instances like this. And within this scope, the most famous MAPF algorithm is called conflict-based search, CBS. I do not explain the mechanism. CBS has been extensively studied, and there are many powerful extensions. As a result, it can solve more instances than A-star variants. In this benchmark, 8.3%, great, but we need to solve more. Now, let's think about relaxing the optimality, but this time we do not allow arbitrary solution quality, rather we allow bounded suboptimal solutions. This means that we can still provide solution quality guarantees. And let's see the performance of a bounded suboptimal and complete method. Now, A-star-based algorithm can solve beyond 30%. Okay, what happens if we relax both completeness and optimality? There is a powerful CBS variant called EECBS, which is bounded suboptimal. And you can see that this algorithm successfully solved over 50%. Still, it is 50%. We want to solve much more. So let's think about giving up both completeness and optimality. Typical example of this class is called prioritized planning, or PP. Again, I believe that everyone knows prioritized planning, probably, so I skip the explanation. Instead, I want to show you the performance. Prioritized planning can solve over 60% good, but since we drop both the completeness and optimality, we expect more in the performance. Indeed, there is a more advanced algorithm called LNS2. At a very high level, LNS2 repeatedly performs deconfliction between several paths until there is no collision. This idea is very simple, right? But it works quite well. LNS2 can solve 80% of the benchmark instances, so it is capable to address hundreds of agents in a quick manner. Okay, I stopped the introduction of various MAPF methods, but this figure itself is very interesting. We can observe that to solve more instances, we need to drop nice theoretical properties. But who cares about theoretical properties? Solving more instances seems much more important. But there is a pitfall. Let's think about this instance with 4 agents. And agents need to swap their locations in a narrow corridor. Interestingly, scalable methods cannot solve this instance with 4 agents. Rather, non-scalable but guaranteed methods can solve this setup. So my claim is that having good theoretical properties is actually important. Okay, let me summarize the observations so far. There are 2 axes to evaluate MAPF methods. One, having good coordination guarantees, such as completeness or optimality. And 2, planning effort, relating to speed or scalability. Ideally, we want to achieve both, but there's a trade-off. So the question here is that, can we break this trade-off? The answer is yes. Now it is ready to introduce ultra-lightweight MAPF methods, PIBT and LaCAM. When I was young, I liked this puzzle game. Here, we can slide blocks and manipulate their positions to move the red block toward the goal point. And to solve this puzzle, there are two types of people based on planning horizon. On the right side, I provide an intuitive illustration of two types. The first type is, before moving your hand, you simulate all movements in your mind. And once a solution path is found, you start moving your hand according to your simulation result. The second type likes try and error. Such a person is thinking a solution while moving your hand, like this movie. And we can map these two planning styles into the trade-off figure. On one hand, long horizon planning has nice theoretical properties, but it requires significant computational effort and it is typically slow. On the other hand, the short horizon planning has small computational effort, but it cannot be optimal, or sometimes you may miss the solution. If so, why not integrate them to complement each other? This is a bit ambiguous concept, so I want to use this metaphor. If you think about carriage like this figure, there are two components, horses and coachman. Horses have power. They can powerfully advance the carriage, but it is a short horizon manner. We cannot reach the destination only by horses. So we need coachman. Coachman himself does not have power to bring the carriage, at least I cannot, but he can lead horses to the correct direction using long horizon planning. By combining both components, carriage can quickly reach the destination. And this is indeed a nice metaphor for the methods that I will explain. The horse part is called PIBT, and the coachman part is called LaCAM. Let's first look at PIBT. PIBT is a configuration generator. Given a configuration and preferences that indicate which actions are preferable, PIBT generates a collision-free configuration. For example, for this blue agent, the right-going action is preferred because it is heading toward the goal. Now, let's see how to generate a collision-free configuration. To understand the intuition, let's think about greedy allocation following priorities. In this example, if the blue and green agents plan the next location like this figure, then this guy, red guy, has no candidates in the next time step. Right? If this guy tries to go up, then it will collide with blue agent and like that. So this is a stuck situation. To prevent such situation, PIBT first introduced priority inheritance. If a low priority agent is blocking requests from higher priority agent, then the low priority agent temporarily inherits higher priority. Now, this guy, the low priority agent, plans the next location before the green agent. As a result, all agents have locations for the next time step. However, it is still insufficient to prevent all stuck situations. And this is an example. As a result of priority inheritance again and again, the agent on the corner, this guy, gets stuck. To prevent such situations, PIBT introduced backtracking protocol. Backtracking has two types, valid or invalid. Valid backtracking says that you can move there, and invalid backtracking says that you must replan, I will stay. In this example, the agent on the corner has no candidate. Then this agent sends backtracking as invalid. Now, this agent tries to replan solutions. However, this agent has also no location at the next time step. Then it sends backtracking as invalid. Now, this guy replans its next location. And this agent can move to the left side, so the remaining backtracking becomes valid. Now we have a collision-free configuration while reflecting the agent preferences. And this scheme always generates collision-free configurations. From the implementation perspective, PIBT can be efficiently written in a recursive style. And this collision-free configuration generation is really convenient. For example, there is a competition for lifelong warehouse automation called the League of Robot Runners. And this is sponsored by Amazon Robotics, so the competition reflects actual industrial setups to some extent. The winning prizes are huge, 10,000 US dollars, and there were many submissions. I myself didn't participate in the competition, but the winning strategy for this competition was in 2023 was actually based on PIBT. Then what happened in 2024? Well, the default planner became PIBT, and the winning strategy was again PIBT. So I am continuously missing 10,000 US dollars. I'm sad about that, but anyway, this is a good advertisement of PIBT. Okay, although PIBT is one-step configuration generator, it is possible to solve MAPF by iteratively generating a configuration using the previous one as input. And this algorithm is of course incomplete, but if PIBT is lucky, then it can reach the goal configuration quickly. Here is the performance. Recall that this figure illustrates runtime versus the number of solved instances. PIBT can quickly solve many instances, but due to its greedy nature, there are still a lot of unsolved instances. In fact, since PIBT creates a configuration in a greedy manner, it cannot solve this instance that requires to swap locations of two agents in narrow corridor. Okay, this is a limitation of short horizon planning. We need long horizon planning. I first recap A-star. A-star creates a super huge search tree due to the huge branching factor of MAPF. But most of nodes are not interesting, right? Simply wasting time and memory. And this is PIBT. It directly goes to the goal configuration without any additional node generation. This is incomplete, but we add search scheme on top of PIBT. That is LaCAM. LaCAM stands for Lazy Constraints Addition Search for MAPF. It starts the search from the initial configuration, but we cannot list all successors. Instead, LaCAM uses PIBT and creates only one successor. For the next iteration, it picks one node and applies the same procedure. But again, only one configuration is generated by PIBT. And this process is repeated until finding the goal configuration, and once found, backtracking, done. So it is a PIBT-guided depth-first search, but with lazy successor generation. Doing so significantly reduces the number of node generation, and we can immediately get solutions. The crux of LaCAM is how to generate a configuration step by step, and this is done by introducing another search scheme. And for this purpose, LaCAM introduced a constraint tree. Each search node of LaCAM maintains a constraint tree. Each node of this tree has a constraint that specifies who goes where. For example, with this constraint, the blue agent must go to the left side in the next configuration. And during the search, LaCAM can visit the same node again and again, and each time the constraint tree has been developed. For example, at the first visit, the constraint tree has only a root node. This is a special node that has no constraint. Then a configuration generator, PIBT, can generate an arbitrary neighbor configuration. At the second visit, the tree contains a constraint that specifies the red agent must move to the left. Then the configuration generator must follow this constraint. In this way, a constraint tree is gradually developed while generating configurations. The tree construction is done by, for example, breadth-first search. When the tree development is finished, the original configuration has been generated, all neighbor configurations. Therefore, they can perform exhaustive search. Alright, now let's see the performance of LaGAT. In this graph, I show the number of agents versus planning success rate. Neither ASTA nor PIBT can solve any instances with 400 agents, while LaCAM solved all instances. So LaCAM successfully guides a PIBT towards the goal configuration. Let's back to this figure. Notably, with fine-tuned PIBT, LaCAM successfully solved 99% of the benchmark instances within 10 seconds. In fact, this result extends the frontiers of search-based MAPF methods significantly. Before LaCAM, to be scalable, we need to lose nice theoretical properties such as completeness or optimality. However, LaCAM has good theoretical properties and it also achieves high performance. As a result, it can do something crazy like this. LaCAM suboptimally solves MAPF for 10,000 agents with many narrow corridors in a few seconds on my laptop. This was a super crazy instance for conventional search schemes, but now it is possible to solve this. Alright, we now have quick and scalable methods. Are you satisfied with these planners? I'm not satisfied. Solution quality is also important. Here, I share my concerns of LaCAM. I picked up a specific map from the benchmark. There are 25 instances, and the vertical axis represents the solution quality for each instance. I tested LaCAM and LNS2. As you can see, although LNS2 fails to solve many instances, but if it solves the instance, the quality is better than LaCAM. LaCAM solved all instances quickly, which is great, but the quality is not so remarkable. Now, we have another trade-off between solution quality and scalability. Typically, there are two approaches to challenge this trade-off. The first direction is improving the scalability of optimal methods. The second direction is to improve the solution quality of suboptimal methods. And for this purpose, vanilla LaCAM is indeed a good starting point. So let's do engineering LaCAM towards real-time, large-scale, and near-optimal MAPF. There are two directions to improve the performance of LaCAM. The first direction is to improve the initial solution quality, like this green arrow. And the second direction is to improve the convergence speed toward optimal solutions. By these combinations, we can expect to find near-optimal solutions by the planning deadline. And once you have done a good engineering, the effect can be remarkable. Here, I show a visual comparison between LaCAM 2, which is a vanilla LaCAM, and LaCAM 3, an engineered version. And you can see that the engineered version is much better compared to the vanilla LaCAM. How can we achieve such a good planning? One simple technique is to improve tie-breaking in PIBT. Recall that PIBT uses preferences which represent which actions are preferred for each agent. In this example, the preference for this blue agent can be unique, right? While the red guy, this guy, we have two choices because the shortest paths on a graph on a grid are not unique. So we need tie breaking, but this tie breaking actually affects the final outcome as shown on the right side. Using this B, the bottom one is clearly better because the red guy can reach the goal destination, goal point for 3 steps. And based on this observation, we developed an intuitive tie-breaking strategy for PIBT preference. The result is impressive. The red line, this line, represents the advanced tie-breaking. Although there are small overheads in runtime, with 4,000 agents, we achieved 20% improvement in solution quality just by improving tie-breaking. And this is just an example of how PIBT and LaCAM can be improved. We have more techniques. For example, we can apply large neighborhood search, LNS, to define the solution. The idea of LNS is simple. we first select a subset of agents and define these solutions by other MAPF methods, like prioritized planning, and repeat this process again and again. And this gradually improves the solution quality over time. But LNS is an effective post-processing method after getting the initial solutions, but we can apply the similar concept for finding the better initial solution. Specifically, I want to suppress congestion, which is a critical issue for large-scale multi-agent navigation. This is a visualization in continuous decentralized navigation tasks. You can see that on the left, agents get congested and the navigation performance is degraded, while on the right side, the flow seems to be smooth, right? And this is due to the introduction of congestion-aware guidance, and we can construct such a guidance using LNS-like pre-planning. How to do that? There are two steps. In the first phase, we compute spatially scattered paths for each agent. This is done by first computing individual shortest paths for each agent, then repeat path refinement. And this refinement selects one agent and recomputes its shortest path while minimizing the collisions with others to mitigate congestion. And in the second phase, we can run PIBT while making agents follow the pre-computed path as much as possible. This technique is simple, but effectively improves the initial solution quality. On the right side, I show an empirical result with a figure of solution cost versus runtime. And with this technique, for this specific case, we achieved a 12% improvement. Okay, I call this global guidance. Guidance is a powerful concept. It doesn't provide a complete solution for MAPF. Rather, it tries to provide a useful information to MAPF methods to derive efficient solutions. For LaCAM, the global guidance is computed once before running actual search, illustrated like this figure. It's quite effective, but we don't know what happens during the search, this box, right? So the offline guidance could be outdated. Instead, what we can do is to insert the guidance construction within the LaCAM search, like the figure on the right side. That is a notion of local guidance. The idea is again super simple. For each PIBT call, we compute windowed paths while minimizing congestion using soft collision penalty. Then PIBT tries to follow the guidance. On top of that, we can perform LaCAM. And in this video, you can see that the guidance paths are updated as agents move. And this guidance can provide better heuristic for PIBT and LaCAM. And here is an empirical result. The figure illustrates cost versus runtime. And LaCAM is here. Global guidance is with pink, and the local guidance is this blue one. Local guidance has a slight overhead in computation time, but it can significantly outperform global guidance. Moreover, it completely outperforms LNS2. On the right side, I show why local guidance is effective. And this is a heat map showing how many times each vertex is used by any agent. So the warm color represents congestion. And you can see that local guidance suppresses the congestion in bottleneck areas, which results in significant cost reduction. Okay, these are examples of how to improve PIBT and LaCAM. I'm still developing effective methods, and I also believe that other researchers will improve the technical components. But these are developed with human bias. If we want to go beyond, I believe that we need learning techniques. A combination of learning and search could lead to remarkable results. A notable example is a game of Go. This picture is a landmark moment in the history of AI where AlphaGo outperforms the world Go champion. The idea behind AlphaGo is to learn a neural network to efficiently guide the search. And both learning and search are important to achieve superhuman level performance. And this is a qualitative result from the Nature paper. And if you use the search-only approach, you will underperform top players. Maybe it is better than me, but it cannot outperform the top players. And if you use learning only, you will still underperform top players. By using both, the AI agent can outperform the human performance. And I believe that we should have a similar structure for MAPF to design more capable methods. How do we use machine learning in MAPF? A typical approach is to develop a neural MAPF policy. Here, we aim to develop an agent-wise policy that receives local observation, typically represented as a field of view, and we have a neural net that outputs which actions look promising. To train such a policy, people usually use either reinforcement learning or imitation learning. Why these neural policies are appealing? Because this adapts a decentralized style. So we can expect scalable real-time planner that works with partially observable setups. In fact, development of neural MAPF policies are quite popular. In 2024, I wrote a review paper about this, and we listed several representative approaches like this table. They are growing quickly compared to search-based solvers, and to be honest, nowadays I cannot keep track of them. So learning-based approaches have also made significant research progress. But how about the performance? My short answer is that learning-based methods are significantly behind the search-based solvers. The left one is from recent benchmark paper, and LaCAM 3, one of the most advanced search-based solvers, outperforms all learning-based approaches in all aspects. Another RL-based papers also report similar things, like shown on the right side. That is the current status. Okay, how about learning and search? There are several methods like neural-guided PIBT, neural-guided LNS, neural-guided conflict-based search, and so forth. But neural components so far remain an interesting aid. They are not practical at all. For example, the neural-guided PIBT says that all learned MAPF works require non-trivial data collection and complex models, but perform worse than LaCAM. Okay, why these hybrid approaches are not attractive yet? Partially because neural nets are slow. They have model inference time, CPU-GPU transfer time, and so forth. As a result, if we add neural aid to the original search algorithm, they might be able to improve the solution quality, but this wouldn't be enough to surpass the current search-based planners. Until we started doing this research. Now let me describe LaGAT, a successful engineering attempt of learning and search for multi-agent pathfinding. LaGAT is a combination of LaCAM and a neural MAPF policy with graph neural nets, GNN. And this figure shows solution cost versus runtime, which compares LaGAT against LaCAM 3, the most advanced solver to date. And you can see that this neural hybrid approach clearly outperforms LaCAM 3. Okay, here is our recipe. There are 4 steps. We first collect a bunch of solution trajectories using LaCAM 3, and then we pre-train a GNN policy. Then we do a map-specific fine-tuning, and finally we integrate the neural policy into LaCAM with deadlock detection. I will first cover the running part, the left 3 parts. Okay, as a neural policy, we use GNN-based one called HMAGAT. Why GNN is interesting to MAPF? Because GNN can naturally model interactions between agents using message passing. We define communication graph, and each agent aggregates messages from nearby agents to determine an action. This work itself is a bit old and published in 2021, but with appropriate design, GNN imitation learning is still very powerful. And here is an evidence showing runtime versus the number of solved instances. Compared to other learning-based approaches, our improved MAGAT solves more problems much faster, locating on the top. And this is our neural component. So now let's talk about the search integration. And this is recap illustrating LaCAM's search structure. LaCAM uses PIBT to perform exhaustive search over configurations. Inside each configuration generation, we have parent configuration, and we first retrieve cost-to-go values and create preferences for each agent. Then PIBT outputs collision-free configuration, right? And neural policies are easily integrated into this scheme. For each configuration, a neural policy outputs action distributions. And then we can use it to create PIBT preferences. So a neural policy can guide PIBT, therefore it can guide LaCAM as well. That's easy, right? However, neural policies have another trade-off between inference speed and representation power. If you increase the model size, like locating here, it can be expressive, but that's not ideal for LaCAM because LaCAM calls neural nets many times and the search can be super slow. That's why we want to have small neural nets, but such neural nets can be inaccurate, misguiding the search frequently. And this video shows typical behavior when embedding a tiny neural policy into LaCAM. And you can see oscillation, right? Neural policies alone trigger deadlock or live lock situation. LaCAM overcomes this issue with systematic search. Assume that neural guidance incurs such an inaccurate prediction for this blue agent, like this. Right? The goal location is here, but the neural policy, let's say, the neural policy predicts the upgoing action. This is terrible, but it can happen. Then the search continues. The neural policy again misguides the blue agent, but eventually we will encounter the same configuration which has been already appeared in the search tree, and the rollback happens while adding constraints. And this will guide the search into a different branch, and eventually we will reach the goal configuration. Solved. But this is not ideal at all. For this instance, optimal makes 1 is 2, right? So it should be easy to solve. But the good news is that this deadlock or live lock behavior is detectable by checking several ancestor nodes. So once a deadlock is detected, or once a live lock is detected, we can disable neural guidance for specific agents. Then for the next search iteration, standard non-learned PIBT preference is used, and this results in better solutions. Long story short, neural guidance can misbehave, but we can correct this by non-learned component. That is the structure of LaGAT. We tested LaGAT in a dense setup. The left figure shows the number of agents versus runtime, showing that LaGAT here is a bit slower than LaCAM 3 due to the overhead of neural component. Meantime, the right figure shows solution cost, and you can see that LaGAT outperforms LaCAM 3. So LaCAM 3 is here, and LaGAT is here. And LaGAT outperforms LaCAM 3 in terms of initial solution cost, as well as final solution cost at 30 seconds. And this is another visualization of comparing LaCAM 3 and LaGAT. The left plot shows initial solution cost, and the upper left points show that LaGAT finds superior solutions than LaCAM 3. The right plot shows the solution cost at 30 seconds. Collectively, the results suggest that the combination of imitation learning and search can outperform an expert algorithm. What makes LaGAT special? This is the result of ablation study. The left shows the success rate, while the right one shows the solution cost. And according to these results, both pre-training and map-wise fine-tuning improve the planning capability, while neural guidance, deadlock detection, and LaCAM search improve solution quality. So all components were actually necessary to beat LaCAM 3. All right, now we have a decent motivation to study learning-based MAPF methods because it is possible to outperform the purely search-based solvers. Neural processes need to model interactions between agents, and existing work uses a pairwise manner. And this is an illustration from GNN, and clearly interaction modeling relies on peer-to-peer information exchange. But if you are careful, MAPF is actually a group interaction problem. The bottom figure shows a simple example. For this setup, for this blue agent, the stay action is the best one. But this stay action is not derived from any pairwise reasonings at all. This optimal action emerges only when we consider the group interaction. What I want to claim is that the action of one agent is affected by nearby groups, not individual agent. For example, the behavior of this blue agent is affected by the behavior of both red and yellow agents in a collective manner. How do we model these complicated interactions? The answer is to use a hypergraph, which is a generalization of a graph. Based on this observation, we developed a hypergraph neural network policy for MAPF called HMAGAT. The structure follows MAGAT. Instead of communication graph, we first create a directed hypergraph, and based on this, we use a hypergraph neural layer to aggregate messages. Then the policy outputs action distribution to imitate expert trajectories. Performance is strong, and we achieve state-of-the-art performance for neural MAPF policies using HMAGAT. And this result suggests that better inductive biases are key to build small yet capable policies. And of course, if we have better models, our neural hybrid search can be stronger and stronger. Okay, we have capable MAPF ecosystems. That's cool. But our final goal is to conquer the real world by MAPF. So we should confirm whether MAPF can actually handle real multi-robot systems. Actually, multi-robot systems are really challenging. For example, there is a synchronization issue. In this movie, initially small robots are operated correctly, but there were collisions, and once the robots are delayed, the entire system is broken. Another example is this one, using Cambridge Robot Master. They are big. The result is something wrong. We have no way to stop the entire system. Actually, the recording camera was attacked. Even worse, if you increase the number of robots, I'm sure that some robots have troubles. And this movie contains 100 robots, and I have no idea why this robot is rotating. Ground robots are relatively safe, but if you go to 3D, drones are fine. How can we stop them if something's wrong? That's a problem, right? Why this happen? This is because we are performing controls based on our knowledge or assumptions of the real world. Of course, there are reality gaps such as sensor or actuator errors, frictions, and so forth. For multi-robot cases, they will be amplified for communication or individual differences. As a result, robots start crazy movements. But with fast MAPF planner, it is possible to relax these gaps. How to do that? Conventionally, when we think about multi-robot control, we have this kind of picture in our mind. We have global coordinator, and the planner sends waypoints to robot-wise controller. Then the controller is responsible to track the waypoint instruction accurately. We need to periodically update the planning result because the environment or tasks might change. And this feedback loop is typically operated slowly, for example, every 10 seconds, because it was difficult to update global coordination at a higher frequency. But we now have quick MAPF methods. We can operate this feedback loop at higher frequency, let's say 5 to 10 Hz. This means that for each 0.1 second, the system solves MAPF and updates the instruction. As an instantiation of this concept, we developed the multi-robot control framework called LF. LF uses LaCAM to solve MAPF and Flare, a robust optimal trajectory controller, to control holonomic robots. Why this simple architecture is attractive? Because we can easily solve various multi-robot navigation tasks in dynamically changing environments. For example, it is possible to solve 10-drone navigation with dynamic obstacles. Asynchronous target update is achievable. Pattern formation like drone show is doable. Target following while maintaining formation is also doable. All these coordinated behavior is made possible with fast MAPF replanning. By simply running MAPF at higher frequency, we practically solve multi-robot control programs despite reality gaps. As a technical point of view, LF is realized with the direct adaptation of LaCAM to continuous domains. In classical MAPF, the state of the agents are defined by grid cell, but I just put it in 3D spaces. Then actions are defined with rotational motion primitives, and finally, we need to do collision checking in continuous spaces, but that's it. This results in capable multi-robot controller. For example, we can walk through the drone swarm. Here, 15 drones continuously solve one-shot MAPF navigation. And this is me, and my location is tracked by the mocap system. As I am an obstacle, LF controls the drones to navigate them while avoiding me. Well, this was excellent experience, although it's super dangerous. LF is a good example of MAPF feedback control. It can solve various coordination programs, but our hardware is actually much capable. In the right video, one drone is doing crazy movement, but we cannot extract such an aggressive motions with LF. Why? Because we have another trade-off. And this time, we have a trade-off between planning effort and kinodynamic aggressiveness. And this trade-off is dominated by planning representation. For example, on one extreme, we have grid world MAPF, right? Planning is easy, but we will only have zigzag paths, ignoring low-level robot dynamics. On another extreme, we can represent a robotic system as a continuous dynamics equation and achieves aggressive motions, but such a kinodynamic planning is challenging. And LF is here. So the next challenge is this. Can scalable MAPF upgrade this border? Motivated by this challenge, we developed db-LaCAM, an adaptation of LaCAM to kinodynamic multi-robot motion planning. This algorithm can accommodate arbitrary robotic systems. For example, the right video is drone one, while the left example is planning for cars with trailers. db-LaCAM uses full-state continuous representation of robotic systems. It performs planning with motion primitives, a short dynamically feasible trajectory to steer the search. With the advanced collision checking, it is possible to derive solutions quickly than existing methods. And here is an empirical evidence, and this figure includes a bunch of scenarios consisting of car-like dynamics, double integrator models, 3D scenarios, and so forth. Compared to the kinodynamic variants of conflict-based search, db-LaCAM reliably delivers solutions much faster. Of course, it is suboptimal, but we already know that there are many techniques to improve solution quality of LaCAM, so I'm optimistic about this point. db-LaCAM can solve large programs quickly compared to previous approaches. However, you can see that the outcome is a bit jokey. We want to have smoother trajectories. This non-smoothness is due to the motion primitives. db-LaCAM derives solutions by stitching motion primitives, so it is difficult to optimize the trajectories as it is. Such trajectory optimization is achievable with numerical optimization using nonlinear programming. We encode trajectory optimization programs like the formulation shown on the right side and derives a smoother solution. It is possible. It is doable, but it can take too much time. For example, this 9 robot case requires 15 seconds to solve. We need better tools. And I and my colleagues have explored several directions, actually a bunch of directions, and it turned out that the diffusion denoising seems promising too. Diffusion model is capable to capture very high-dimensional data, typically targeting to image or video generation. But we can also apply diffusion denoising to matchable trajectories to obtain smoother kinodynamically feasible trajectories. And based on this belief, we have developed DEFORM, novel black box optimization schemes for matchable trajectories. DEFORM optimizes trajectories by iteratively optimizing deformation control. There is no running component. Instead, the score function in diffusion model is approximated by massive Monte Carlo sampling attempt. Thanks to GPU parallelization, this scheme is much faster than traditional numerical optimization-based methods. For me, DEFORM is just a tool. It is a joint multi-robot trajectory smoothing, serving as a building block for advanced methods. For example, we can do decoupled planning using DEFORM, similar to LNS2, and it can derive continuous trajectories for 100 robots. So we now have nice tools, db-LaCAM to solve kinodynamically feasible multi-robot motion planning, and DEFORM to smooth the trajectories. And I believe that using the advanced MAPF technologies that I introduced so far, we will soon have an innovation in multi-robot domains as well. Okay, wrap up. So I want to solve real-world multi-agent multi-robot programs. To do that, what we need is to crack this MAPF feedback control loop. To do that, today I introduced various tools to make this concept concrete, such as quick MAPF methods, better real-time planning techniques, as well as robot deployment. Now, we have nice MAPF toolbox, and we are almost ready to bring these MAPF technologies to the actual multi-robot systems. Of course, we have many missing pieces. At least some of them, like parallelization, hardware test bed, incremental planning, and so forth. There are challenges, but I'm optimistic because of my experience. For example, in January 2021 at AAAI, I was told as like this: you are interested in pathfinding for 10,000 agents, you are a dreamer. To be honest, I agreed at that time. It seems to be ridiculous. But within several years, I developed PIBT and LaCAM. They can solve pathfinding for 10,000 agents. As a result, what happened? Well, LaCAM has been already deployed in several warehouse companies without my involvement. So my algorithms are controlling countless of robots right now. Therefore, I'm very confident that scalable multi-agent planning step changes multi-robot systems. We continue to strive for more agile, robust, adaptive, and computationally efficient methods. To do that, I am generally open to collaboration if I have bandwidth. Feel free to contact me if you have any questions. Last but not least, I would like to acknowledge my advisors, collaborators, funding, as well as the wonderful MAPF community. That's all. Thank you for kind watching.